We're finally going to look at actually finding absolute maximum and absolute minimum values of a function. Absolute max and min values of a function. And just so I'm not misleading you, we're not going to be looking at the absolute max and min of a function on its entire domain. We're going to start basic and limit our discussion to absolute max and min values on a closed interval. And to do that, we need to understand this very basic theorem called the extreme value theorem. Maybe it has other names as well, but we're going to call it the extreme value theorem. And it says something very basic. It has one hypothesis. All we have to assume is that some function f is continuous on a closed interval. So if f is continuous on the closed interval from a to b, about the most basic assumption you can make in calculus for any theorem. If you have that, then this theorem guarantees that f attains an absolute max value and an absolute min value on this closed interval from a to b. So somewhere from a to b, at a or at b, this function is guaranteed to have a maximum value and an absolute minimum value. If we look at a picture of this, you'll see that it's pretty obvious that that could happen. So let's say that this is a and this is b. And if I've got a continuous function over the closed interval, then that means my endpoint over here at a has to be a closed endpoint. And as I graph from a to b, I can't have any gaps or breaks. So it has to be a continuous graph from a to b. So some of it might be smooth like this, some of it might be jagged like that. Okay? And so this function is continuous on the closed interval from a to b. It's not differentiable because we've got this sharp corner here, so it's not differentiable, but it's certainly continuous on the closed interval from a to b. And so this extreme value theorem guarantees that we will definitely have between a and b an absolute max and an absolute min. And you can see that if you look over this interval, we have a highest point right there. Okay? So it definitely has an absolute maximum value, and that would be whatever the y value is for this point. All right? And it also happens to have an absolute minimum value, and that would be the lowest point, which appears to be right here. And so the absolute minimum value would be the y value at this point. Okay? So this theorem guarantees this property of continuous functions on closed intervals. Now, that does not help us understand how to actually find, without a graph, how to actually find the absolute max and min on the closed interval. So that's what we want to explore next. And we can kind of understand through this picture. How do we know where to look for absolute max or absolute min? Well, we definitely want to consider any place where the function has a horizontal tangent line. Because when that happens, we might have at least a relative maximum or minimum. Okay? Maybe not absolute, but it could be an absolute. So we'd consider this point. We would also consider this point for the same reason, it has a horizontal tangent line. In other words, the derivative equals 0. And don't worry about copying all of this down, all these words that I'm saying. We're going to summarize this nicely after we give a basic discussion here using this graph. So we want to consider any place where the derivative equals 0. We also want to consider any place where the derivative does not exist. Any sharp points, the derivative does not exist. Anytime you have a vertical tangent line, the derivative does not exist. Okay? If it's not continuous, the derivative does not exist. However, for this theorem, we have to assume it is continuous. So we don't have to worry about that condition. So we look for places where the derivative equals 0. We look for places where the derivative does not exist. Those are all good candidates for finding your absolute max and min. The last places we look are they're kind of unique on this graph. We have to consider the endpoints. The endpoints are likely to be, not likely, but they should be considered as candidates to give you your absolute max or min, just like this point here was our absolute min. Right? This was our absolute min. This was our absolute max. And they fall into one of the categories we discussed. Here we've got a derivative that equals 0. Here we've got an endpoint. Okay? So let's summarize this now. We understand this basic theorem that guarantees when we will have an absolute max and min. Now let's summarize how to find the absolute max and min of a function without a graph. So to find absolute max and min of a continuous function on a closed interval. Okay? So if you've got all those conditions, which aren't that rare actually, many functions are continuous everywhere. So it's not that rare to have a function that's continuous on some closed interval. But how do you find an absolute max and min of a continuous function on a closed interval? Let's put a comma. Consider the following x values. These might be good locations to look for an absolute max or min. In fact, they will occur at one of these x values, okay? They're guaranteed to exist, and they will occur at one of these x values. So you want to consider where f prime of x equals 0, right? That's what we talked about before, where you have a horizontal tangent line. That's a good place to look for an absolute max or min. You also want to consider where the function is not differentiable. In other words, consider where the derivative does not exist. Where f prime of x does not exist. That's where the function is not differentiable. The last place you want to look are the endpoints. Okay? Look at the endpoints. So we can make this more concise even. We could say f prime of x equals 0, f prime of x does not exist. But that's the same thing as saying critical values. Critical values. So when you want to find absolute max and min of a continuous function on a closed interval, look at the critical values and the endpoints. It's that simple. Okay? To find the critical values, of course, you're going to have to find the derivative and do some algebra to determine those x values. All right? So let's get started. Let's put all this together and see how it works with a few examples. So we'll do probably 3 examples. Find the absolute max and min values. Find the absolute max and min values on the given interval. Find the absolute max and min values on the given interval. So example 1, we'll do a very basic function to begin with. Example 1 is just going to be a polynomial function. F of x equals, how about x cubed minus 6x squared plus 5. And we will look at the interval from -3 to 7. Okay? Look at the interval from -3 to 7. So now, the first thing we need to know, and it doesn't mention in the instructions, but the first thing we need to know is, do we know for sure that this function has an absolute max and min on this interval? Well, we can go back and reference the extreme value theorem. If this function is continuous on this interval, then we are guaranteed. So let's talk about the continuity of this function. It's a polynomial function. This guy is continuous on its domain, which is all real numbers. It's continuous everywhere. So it's certainly continuous on this smaller closed interval. So that's good. That means by the extreme value theorem, this function definitely has an absolute max and an absolute min on this interval. So let's find the absolute max and min values. To do that, we need to consider three things. Really two things: critical values and endpoints. So let's do the hardest part first. Let's find the critical values. The critical numbers. Okay? For the critical numbers, we're going to have to know the derivative. So let's look at f prime of x. The derivative here is pretty simple. It's just 3x squared minus 12x. So we're going to have to decide where f prime of x equals 0 and where f prime of x does not exist. Okay? Let's go ahead and talk about where f prime of x does not exist. F prime of x is a polynomial. It exists everywhere. So this condition doesn't happen. There's no x values for which f prime of x does not exist. F prime of x exists everywhere here. You can't plug any x value into this and not get an output. Okay? But where does f prime of x equal 0? Well, we have to solve the equation 3x squared minus 12x, f prime of x, equals 0. And so probably the easiest way to solve this is to factor. We could pull out a common 3x, leaving behind, if I pull a 3x out here, I get an x. If I pull a 3x out there, I get a minus 4. And so we can see that x could be 0 or x could be 4. Okay? So our critical numbers are 0 and 4. Those are good candidates for where we might have an absolute max or min value. Okay? The other place we need to look besides critical numbers are the endpoints of the interval. The endpoints. Those are easy. Those are -3 and 7. So now what we have to do is for each of these x values, we have to figure out which x value has the highest y value and the lowest y value. So we need to find the y values for these x values by using the function. So we have to calculate f of each of these four. So let's look at f of 0. F of 0 is easy. You just get 0 plus 5. Let's look at f of 4. 4 cubed is 64. 4 squared is 16. So 6 times 16 is 96. 64 minus 96 is -32, plus 5 is -27. Okay? Now we have to look at the endpoints. So let's look at f of -3. -3 cubed is -27. -3 squared is 9. 9 times 6 is 54. So -27 minus 54 is -81. Plus 5 is -76. Okay? And last, we've taken care of 0, 4, -3. Let's look at f of 7. This one I'm going to get the calculator out, just in the interest of time. So 7 to the third minus 6 times 7 squared plus 5 appears to be 54. So if we were to graph those points, right? If we were to graph those points, just to get an idea of what this is telling us, We're going on the closed interval from -3 to 7. The output for -3 is -76. So that's -76 is its y value. The output for 0 is 5. So that's at 0. The output is 5. The output at 4 is -27. And the output at 7 is 54, maybe like up here. So we can see that the absolute maximum is 54 and the absolute minimum is -76. And we even can kind of picture a little bit about the graph by looking at the points. Okay? But we don't have to do that. I just wanted to show you this first time. Much later, we're going to actually be graphing functions using derivatives. But for now, we can say, all right, -76 is the absolute minimum value. And it occurs at -3, of course. And 54 is the absolute maximum value. All right? And it occurs at 7. All right, let me just check our time of our video here to see if we have time for 2 more examples. I think we'll be okay. All right, so that's a basic example, getting warmed up with this concept of critical numbers and endpoints to find absolute max and min, just a polynomial. So let's look at some other types of functions. The next one, let's look at a rational function. So we're still going to do the same instructions, but this will be example 2. So this time, let's look at f of x equals x over x squared minus x plus 2. X over x squared minus x plus 2 on the closed interval from 0 to 4. Okay? And so now we've got the hang of this. If I want to know if this has an absolute max and min, for sure, I could use the extreme value theorem and that could convince me. So in other words, I need to know where this is continuous. Well, this is a rational function. It's continuous on its domain. So the question becomes, what is its domain? Well, the domain of a rational function simply excludes the values that make the denominator 0. We can't divide by 0. So we need to figure out where the denominator equals 0, and that's going to tell us the values that x can't be. Those are going to tell us the places where f is not continuous. So x squared minus x plus 2 doesn't factor in the traditional sense, but we could solve this quadratic equation using the quadratic formula. So we get x equals negative b, which is positive 1, plus or minus the square root of b squared, which is 1, minus 4 times AC. AC is 2. And that's all over 2 times 1, which is just 2. And so right here, we always like to look at what's under the square root. That's called the discriminant. In this case, 1 minus 8 is a negative number. So the only x values that will make your denominator equal 0 here are imaginary x values, meaning that the domain of this function is every real number, because every real number will not make the denominator 0. There's no real number that you could plug in here to make 0 on the bottom. So you can plug in any x value you want and you're okay. You just have to avoid these 2 imaginary numbers, which we're not considering anyway. So the good news is this function is continuous everywhere again, just like our last example, but it took a little more work to see that. And so if it's continuous on negative infinity to infinity, then it's certainly continuous on this closed interval. And by the extreme value theorem, we are guaranteed to reach an absolute max and an absolute min on this interval. Okay? So we know we can do it. So let's get down to that business. So we need to know the critical numbers. If I want to find the critical numbers, I have to find the derivative and then determine where it equals 0 and where it does not exist. So I need to know f prime of x. To differentiate this, I have to use the quotient rule. So I'm going to have the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 2x minus 1. And that is all over the bottom squared. And let's just simplify this down a little bit. Here I'll have to distribute my negative x. And then I can combine like terms. So I've got x squared minus 2x squared, which gives me negative x squared. I have negative x plus x, that's 0. I have 2, and that's my only constant, so plus 2. And all of this is over x squared minus x plus 2, quantity squared. Okay? So now I have to figure out where f prime of x equals 0. And so this is my f prime of x. It's a fraction. A fraction only equals 0 if the numerator equals 0. So I have to figure out where negative x squared plus 2 equals 0. So I'll add x squared to both sides. And I'll take the square root of both sides, remembering to consider the plus and minus square root. However, I'm only interested in absolute max and min on the closed interval from 0 to 4, and the negative square root of 2 lives outside of that interval. So I'm going to restrict this down to where I'm only interested in the positive square root of 2 x value. So that's a critical number. The square root of 2 is a critical number. Okay? I need to look at where f prime of x does not exist for the other critical numbers. Well, f prime of x, again, is this fraction which won't exist when the denominator equals 0, right? So this denominator will only equal 0 if x squared minus x plus 2 is 0. And we already saw that x squared minus x plus 2 will not equal 0 no matter what real number you plug in. So this is impossible. F prime of x exists everywhere. It's differentiable everywhere. So that doesn't yield any critical numbers for us. Okay? So we have all of our critical numbers now. All right. So I can erase all this work. We've got our critical numbers. If I had a bigger whiteboard where you could see it all, of course I'd leave all the work. You wouldn't just go erase this on your paper, right? But we need to do some more work, so I'm going to erase and keep the important stuff. So I've got my critical numbers. There's only one. And I also have to consider my endpoints. Okay? My endpoints. My endpoints are 0 and 4. Now I've got to look between these three x values and figure out which one has the highest y value and the lowest. So I need to look at let's look at f of the square root of 2. And I will go to my calculator for that. So on the top, I've got the square root of 2. And on the bottom, the square root of 2 squared is just 2. So I've got 2 minus the square root of 2 plus 2. And so as a decimal, well, first of all, without a decimal, this is the same thing as 1 plus 2 square roots of 2 over 7. Okay? 1 plus 2 square roots of 2 over 7. And just to get a rough idea of what number that is, it is about 0.55. Okay? Just to get an idea. We can come back and do more digits if we need to, as far as rounding it. So that's f of the square root of 2. So I've got the y value for that guy. Let's look at f of 0. That's easy. I get 0 on the top. I get 2 on the bottom. 0 over 2 is just 0. And now I've got my y value for this guy. Last, I need to know f of 4. So I get 4 over 16 minus 4 is 12, plus 2 is 14, and that's 2/7, which as a decimal, just to get an idea, 2/7 as a decimal is about 0.29, okay? So if I'm looking at the three y values, then the biggest y value is actually pretty small. This is the biggest. This is the biggest y value, and the smallest is 0. Okay? So we would say, you want to be careful, we don't want to say 0.55 is the absolute max value because that's incorrect. That's an approximation of the real absolute max value, which is this. So we can say 1 plus 2 square roots of 2 over 7 is the absolute max value. Of course, it occurs at square root of 2. And we can say that 0 is the absolute min value. Okay. So that example maybe is a little more interesting than the polynomial example for various reasons. You had to use the quotient rule. When we found the critical numbers, we didn't keep one of them because it didn't fit in this interval. We had a square root that we had to deal with on the calculator. So a few different things there in this example. Okay? Let's do one last example, and we'll call this video done. So we'll look at example 3. Example 3 is going to be made up of two different types of functions. So example 3, let's say f of x equals, how about 3 times the cube root of x minus x. All right? And so let's look at that on the interval from, how about -3 to +3. All right? This function, its domain is all real numbers. It's simply a cube root function subtracting a polynomial function. Everything here has a domain of all real numbers. It's continuous on that domain, which includes this closed interval. So the extreme value theorem tells us we can actually find an absolute max and min on this interval. So let's get to it. If I want to do that, I need the critical numbers, of course. The critical numbers. So I have to determine where f prime of x equals 0, where it's undefined or does not exist, but I need to know the derivative first. So this is x to the 1/3 power. So I've got my coefficient of 3. And if I do the power rule, I'll bring my 1/3 power down to the front times x. And then the 1/3 power has to subtract 1 to give us -2/3. So we've got 3 times 1/3 x to the -2/3 power minus the derivative of x is 1. Okay? So f prime of x equals, luckily 3 times 1/3 is just 1. So we just get x to the -2/3 minus 1. And if you want, you could think about that as being 1 over x to the +2/3 minus 1 if you like. Either way is perfectly fine. But now we need to know where f prime of x equals 0 and where f prime of x is undefined or doesn't exist. Okay? So I need to figure out when this guy equals 0. 1 over x to the 2/3 minus 1. When does that equal 0? So we're going to add 1 to both sides. However you want to think about this, you could take the reciprocal of both sides, or you could multiply both sides by x to the 2/3, whatever algebra makes more sense to you. But in either case, you're going to get x to the 2/3 equals 1. And so now, how do we get rid of a 2/3 power? Well, what we do is we can raise that to the reciprocal power. So I could raise this to the 3/2 power. And if I do it on the left side, I have to do it on the right side also. Take the 1 and raise it to the 3/2 power as well. And then you can see that the exponent properties say, well, we multiply those exponents and we get x to the first power. So that's a simple way to do that. So we just get x equals 1 to the 3/2 power, which is 1. So 1 is a critical number, okay? Now, where does f prime of x not exist? Where is it undefined? So I'm going over here and looking at this guy and asking, when does this not exist? Well, this guy would not exist if x were 0, because I'd be dividing by 0 in this fraction. So if x is 0, I can't calculate an output for this derivative formula. So 0 is also a critical number. And both of those happen to fall in this interval, so we have to consider both, okay? All right, so those are our critical numbers. Kind of an interesting example here, especially with the exponents, to kind of see what happens there. We also need the endpoints, so let's list those, and then we will start testing. So we need the endpoints. -3 and +3, okay? So now we need to find out all of the y values. So let's find f of 1. F of 1's pretty easy. The cube root of 1 is 1. 3 times 1 is 3. And 3 minus 1 is 2. So we've got the y value for 1. Let's look at f of 0. 3 times 0 is 0, minus 0 is 0. So we've got that one also. These guys are going to require a little calculator work. So let's find f of -3. So I need 3 times the cube root of -3 minus -3. Let's go ahead and type that in and see what we get. 3 times the cube root of -3 plus 3. And that is about -1.33, okay? Let's look at f of +3. Same idea, just plug 3's in instead of -3's. So let's write it out. So we'd have 3 times the cube root of +3 minus +3. And that's about positive 1.33, okay? And so when we look at these, our lowest value, so we tested both of those, our lowest y value occurs at f of -3, and our highest occurs at f of +3. So those are going to be our absolute max and min. So we can say that 3 times the cube root of -3 plus 3, right, that's what this is the absolute minimum value. Sorry about that. This guy's not our highest value, right? I somehow bypassed my 2. And 2 is the absolute maximum value. And we also know the x values at which both of those values occur. And that is the last example of finding absolute max and min. In each of the three examples, we first verified that we knew that there was an absolute max and min using the extreme value theorem, reminding ourselves of properties of continuity and domain. Then we had to find the critical numbers and the endpoints, a good review of critical numbers using the derivative, various types of derivatives, and then evaluating at the critical numbers and the endpoints to find the highest and lowest y values.